This video is part of a three-part series on Air-Fuel Alliance wireless charging measurements using an oscilloscope. Now, the standard we're talking about is based on magnetic resonance, which operates at 6.78 megahertz. This particular video, which we call Part 1, is focused on making current and frequency measurements during the power transfer state. These are pretty simple measurements, but I think you might learn something, a few hints during this video. The first step in making any measurements, any current measurements, is first of all, connect the current probe up to the scope. Do not connect it to your DUT. You need to calibrate and degauss the probe. Now, first of all, make sure it's fully locked. If you go into the channel menu, select probe, and then say calibrate probe. The first thing it will do is it will automatically degauss the probe. And then there's a slight pause. And then it's going to do an automatic offset calibration. This is the offset calibration. Now at this point, our probe is calibrated. But something you should be aware of is you do need to occasionally degauss the probe. It can build up a magnetic field which will cause a DC offset. Now there are ways we can remove the DC offset in the measurements, and we'll show that in a few minutes. But if you just want to occasionally degauss the probe, there's a button on the probe. Just press the button and it will degauss. You really don't need to perform a new calibration, which includes the offset measurement. Now at this point, we're going to connect up to our circuit. I don't have an actual magnetic resonance DUT, but I do have an arbitrary waveform generator that I've set up some signals to simulate real signals on a magnetic resonance charging system. So let's get started making measurements. So I've got my probe connected to my arbitrary waveform generator, which is simulating my probe connected to the PTU coil. I've got the scope initially in a default setup. The first thing to do is to optimally scale the waveform. We can move the volts per division up, seconds per division. There you can see a couple of divisions. This is only taking advantage of 1/4 of the scope's A to D converter. We need to set it up for as close to full scale as possible. This is a pretty good setting here, but that's clipped. That's a good setting. Now you can optimize it by pressing the channel 1 button. Then you have a fine control so you can get the absolute best setting. Now the number of cycles across screen for the best measurement is a little over 100 cycles, so about 2 microseconds per division is the best setting. Now let's perform a frequency and RMS measurement on this current. But let me back up. One thing I forgot. Let's go into the channel menu. The default coupling is DC coupling. You should select AC coupling, and if there's any offset occurring on the current probe, perhaps it's building up a magnetic field, AC coupling will block that DC component and give us more accurate measurements. Now let's make our measurements. We'll select measurements. The default when you select measurements is frequency and volts peak to peak. We've only got 3 digits on the frequency. That's not quite enough. We really don't care about volts peak to peak. Let's clear that one. We'll come back to the frequency measurement. Now let's add a current RMS measurement on this waveform. And you can see right here we have 4 different RMS measurements. There's DC RMS, sometimes called true RMS, and AC RMS. Either one will work, but the AC RMS will eliminate any DC error perhaps contributed by the scope. Now there's also in cycle and full screen. What we want is in cycle, so the RMS measurement is performed across an integer number of cycles. So let's add that measurement. And there we're measuring about 515 milliamps with about 100 microamps resolution. You can see the standard deviation here is about 72 microamps. The number of cycles that's performed across, we can add a measurement just for curiosity to find out what that is. The number of cycles is about 135. The conformance specification talks about making the measurement based on 100 measurements. You could average 100 times, but it's better just to get over 100 cycles on screen, and there's your measurement. Now let's go back to the frequency measurement. The specification is 6.78 megahertz plus or minus 15 kilohertz. This doesn't give us enough resolution. We have a built-in 5-digit counter that gives us 5 digits of resolution. And there you can see it's rock solid, but that's basically because I'm using a generator that has a very stable time base. Thanks for watching this short video on making current and frequency measurements during the power transfer state. Now we have 3 application notes that provide more details as well as step-by-step instructions. I encourage you to download them on the URL listed on your screen. And if you haven't seen the other 2 videos on these wireless charging measurements, I encourage you to watch those as well.